Welcome to Virtual Humans, Lecture 6.2, Fitting Simple to Images with Learning. So the goal is to estimate the simple model from a single image of a person. We saw in the previous lecture that this challenge could be solved by fitting the simple model to images using optimization. We saw that fitting the model to images requires predefined features, being like key points or silhouettes or edges, which are in the first place not always easy to obtain. And optimization can be slow. And to that point, I should say it can be slow if you have a bad implementation, but typically you can also make it fast. And so usually optimization is slow because it's difficult to have a very good implementation. Just as a note, if you see like that optimization is slow, it really depends on the implementation you're using. It gets stuck into local minima, and this is very difficult to avoid. You need very good initialization in order to obtain good results. So the question that we will address in this lecture is whether we can learn a mapping directly using deep learning, like from pixels to the simple model parameters. So the first challenge is that there is a lack of 3D data. We do have data sets where we have paired data of images and 3D poses, but these data sets look like this. Like they typically look like indoor in a lab setup and not very natural. When we go to the real images that you would find on the web, those images they are not annotated with 3D. And if you even look at more complex images with complex interactions and objects and so on, it's even harder. And the reason is that the problem is really hard. It's really difficult, even with manual annotations, it's really difficult to lift this, this pose and shape from single images. And by now, this should not surprise you. We have this depth ambiguity, like the different 3D explanations can project well to the image. And that's what makes it particularly hard. So, okay, so we have some data which is paired, and then we have lots of images. And the question is like, can we learn a prior using unpaired 2D, 3D data? And so it's interesting because in the community, like there were at least 4 papers that came up with very similar ideas at the same time. And this is not uncommon. It's something that happens. Like you go to conferences, you talk to the same people, like the state of technology arrives at the given point, and different groups start working on similar problems, and then some ideas come up at the same time. So the basic idea here is to leverage like 3D data, which is unpaired, and leverage lots of 2D data, which contains, for example, annotations of key points, but in 2D, but not in 3D. And now the question is like, how can you leverage these data sources in order to lift from pixels to images? And I'm going to explain 2 of these papers because I think with these 2 papers, you will understand the key concepts behind this idea of self-supervised learning of pose and shape. So let's start with the first paper, which is called End-to-End Recovery of Human Shape and Pose, which is abbreviated as HMR. So here the authors pose the question directly, like how can we learn a deep neural network to directly regress simple parameters without any paired 3D supervision? So we have here like an encoder and that basically, or a regressor that predicts the pose, shape, and camera parameters of the given image. And if we have no training data, that mapping cannot be learned. So how can we do this? Well, we do have 2D key points in the images, and this was provided by an algorithm that is called OpenPose that worked really reliably at that time. And this gave like this feature, which is very strong but it's in 2D, right? So now you could train this network to go from pixels to the parameters of the simple model, what you have here. And then like you could project the simple model back into the image and minimize this reprojection loss between the predicted joins of simple in 2D and the joins that are detected in the image. Now, what happens if you just train this network naively is the following: like the network produces monsters, and that's fine. These monsters do project to the key points. This is what the network has been trained on, but they do not look like real humans. Now, it shouldn't come as a surprise because the network has not been trained for this purpose. It has been trained to reproject to the 2D key points. But we can be smarter about this, right? And we can leverage large 2D data sets that contain key points and like also data sets that contain 3D poses. These 3D poses are not, or 3D pose and shape are not paired with images, but still we can learn a useful prior from this. And we have seen already a couple of examples on how to build priors. So basically the idea is to explain the 2D data while remaining in this distribution of pose and shape, which is given by the scans. So how can we regularize the predicted simple model? Well, we have seen that pose and shape priors when we saw the registration lecture, and this is not different. You can build a pose prior, you can build a shape prior from the data set, for example, a Gaussian mixture model, or a prior based on variational autoencoders. In this case, the authors decided to go with GANs. It has never been compared HMR with like a simpler prior. That's the choice of that paper, but in any case, that's perhaps not the most important part of the approach. So I should say here, I'm not sure if the GAN is really necessary here. Maybe some simpler priors could have done the job as well. We will see that there's other architectures that, other priors that also do the job. In the next paper, we will see. So basically here, the idea is that the encoder or the regressor will predict like the pose, shape, and camera parameters. And these parameters will have to pass the check of a discriminator, right? That's the idea of a GAN. If you don't know GANs, I suggest that you check what's the principle behind this. So basically, you'll have here the generator, which is given by this encoder that will produce the pose and shape, and the discriminator will decide whether this is a real human or not, right? So you will feed the discriminator sometimes with a real data distribution, sometimes with the encoder distribution. And this is going to be like a game played between the generator and the discriminator, such that at the end of the game, right, once the thing has converged, like the generator produces poses and shapes from the distribution. And then basically like at test time, you just throw away this discriminator and you only retain the generator. So the adversary, right, during training learns about body pose and shape, right? And it makes it harder for the generator, right? It's basically it makes it harder and harder for the generator to fool the discriminator. So using this approach of trying to explain the image while staying within the distribution, the results were at that time quite remarkable. We hadn't seen anything like that for these images in the wild. So this was these were quite interesting and remarkable results in the wild images. Now, one remaining problem is that this approach uses the full pixels, full image with all the pixels as input. And we've seen that there's a huge variability in terms of types of colors, textures, colors, lighting, and different appearances. And so you will need a lot of data for this approach to generalize well. So With this, I will now come to the other paper I want to present, which is neural body fitting. So this is unifying deep learning and model-based human pose and shape estimation. And you will see that this has a lot of similarities with the other paper, but there's a couple of key concepts that are also important that are not present in the other paper. So basically, this paper it presents a very similar idea of self-supervised learning, and it comes from a different angle. So basically, like, it's motivated from looking at model-based approaches versus learning-based approaches. So if you have to fit a 3D model to images, for example, you could match key points and you could minimize this objective function, which measures the predicted key points from the simple model Z hat and the key points detected in the image, right? And so you minimize over pose and shape. And similarly as with registration, or even more so here, because you don't have the depth dimension, the optimization can be slow and complicated at times. And more importantly, it requires initialization. And learning-based approaches, basically, if you have the training data, you can train a regressor. But we've seen that obtaining this training data of images in the wild, natural images with pose and shape annotations, is not easy to obtain or almost impossible. And also one thing that is also very important, and this is true for most deep learning models, they make a prediction and they will never verify against the input whether this prediction is consistent. Right, this 3D output is never verified against the image. And this is a problem because oftentimes the regressors are not very well aligned with the image. We will see how to address this problem later on. But in principle, those regressors are not aligned with the image. So here what it was proposed is basically like the authors realized, okay, this training data is hard to obtain. Key points are easy to obtain, and similar as HMR, they basically use the simple model as an intermediate representation of the 3D world, and then they basically project the 3D key points into the image and compare the 2D key points. And what is interesting about this hybrid architecture is that you can place the loss wherever you want. You can place a loss over the pose and shape if you have a little bit of 3D data, or you could place it here, right? You could place a loss on the mesh vertices of the simple model, or you could place it on the 2D key points when you do not have 3D annotations, when you only have like these key point detections. So this is very similar to these other papers. This paper goes beyond into dimensions. So basically, they pose the question, well, is it useful to use an intermediate representation? So is it useful to simplify the image? Sorry, here there should be an image. Is it useful to simplify the image into a semantic segmentation of the person, for example, and then regress from there? It seems intuitive, right? Because we're removing a lot of the appearance that will make it hard for the network to generalize. And this basically retains the essence of the pose and shape. So all the information about pose and shape seems to be present in this segmentation. But is that true, right? And then this is the question that you have to empirically validate. And then like the other question is like, okay, we do have a little bit of images paired with 3D data, and we have lots of images of key points. And the question is like how much 2D versus 3D supervision you need to train these networks, right? So like, can we empirically validate how much of this 3D data is necessary? So again, this idea of simplifying the image into semantic segmentation comes from this fact that basically RGB images contain lots of variability. And so basically it makes sense to abstract the appearance away. And the other problem that is addressed is that the 3D data is scarce. So let's look at the first problem, which is this input representation, which like trying to find an input representation that will make it easier for the network to generalize. So if that's true, like the question that naturally arises is which representation is good? Is it a silhouette sufficient? Is it like a semantic segmentation into body parts sufficient? Or key points are sufficient? That's a question, right? So let's look at this. And in this paper, this is very carefully evaluated. So basically, here this error bars, they plot the error in millimeters, 3D error in millimeters, that is produced by regressing directly from pixels. So we have 98.5, which is quite high. And if we simplify the image into a silhouette, we have 95.5. And if we now use like a 3-part segmentation, the error is reduced already to 36.5. So this error reduction is very significant, which is telling us that, you know, if you abstract away like a lot of information, then like you can gain some accuracy because you will generalize better, because then the test set and the training set will look more similar, but you went too far, right? You removed too much information in the silhouette, and therefore like the regressor does not work as well as it could. If you don't abstract away so much and you have only 3 parts, then you can do quite well. And this can be further reduced if you use 6 parts and 12 parts. So the reduction is quite significant, from 98 to 27.8 millimeters. And if you use joints, actually you do quite well, but not as well as if you have the full shape, and so on. And this is more or less the same story for another data set. So these are 2 different data sets. The United People is more images in the wild. The human 3.6M data set is more, it's an easier data set. And perhaps that's why the RGB image for this data set is already fine. 48.9 is not great, but it's definitely like much better than this 98.5. So this is illustrating that when you do not have a lot of data, like it's very important to abstract the information that you think is not relevant for your task. And it is very common that you will not have sufficient data for your task. So it's good to think about what the input representation should be, not only to make the regression easy, but also to make it generalize, right, to the test case. All right, so now we will work with part segmentation. And of course, this is an experiment that was done using ground truth segmentation. And now let's look at how important it is to have like a good segmentation. So one message here, when you're doing research, it's very good to isolate the confounding factors, basically. So if you have, you want to analyze how important segmentation is versus another feature, it's good that you start like with ground truth, and then you evaluate how important it is to have a good prediction. And like this, like you're not mixing the factors, right? You could, otherwise you're looking at 2 things at the same time, like how useful the semantic segmentation is versus how easy it is to obtain a good semantic segmentation, right? Both things are important, but it's good to separate. So, okay. So just as a note on how to do good research is like, it's good to isolate the effects. So, okay, given that we know that semantic segmentation is promising, now the question is like, how accurate does it need to be, right? I mean, that's a question. Semantic segmentation in principle is like key points. It should be easier to obtain because it's easier to obtain 2D annotations, right? It's easier to annotate images in 2D. Therefore, it's a feature that is relatively easy to obtain. Okay, so here, like in this paper, they compared different types of segmentations. based on different models. So based on different deep learning models like BCG, ResNet, RefineNet, and so on. RefineNet was the more accurate segmentation, semantic segmentation. And as you can see that the more accurate the semantic segmentation, the better the error. It's perhaps concerning that, of course, like if you go from a prediction, the difference in error in comparing a prediction versus ground truth segmentation is quite significant, right? We're going from 82 to 27.8. I mean, 27.8 is a really, really low error, right, for 3D pose and shape estimation. And here we have the result for an image, and we see that this error is still very high. So it still pays off to get a semantic segmentation, but it needs to be at least relatively accurate, right? If we have like a not very accurate semantic segmentation, we'll do even worse than using the original image, right? Which it's very intuitive, but it's important to validate this empirically. So let's look at how, like more quantitatively, how this affects. So basically on the y-axis here, it's plotted like the accuracy in segmentation. So higher is better, is the F1 score. 1 is the best you can get, and 0 is the worst. And here's the joint error. And so basically we expect that the better the segmentation, the more up in the plot we are, the lower the error. And this is what we observe here, right? It's going in this corner. And the worse the segmentation, the higher the error. So we have an almost perfect linear correlation between the error in segmentation and error in 3D pose estimation. So, well, the message is that you need a good semantic segmentation method in order to do well on 3D pose estimation, especially on these low data regimes for 3D pose and shape. Okay, so these are the messages. Like, use part segmentation as an intermediate representation. If you do not have a lot of data, that's always a good idea. And good segmentation is crucial in order to obtain good 3D pose and shape estimation. But in principle, obtaining a good semantic segmentation should be easier because this requires only 2D annotations and not 3D annotations. All right, so now we've addressed the first question. How do we use 2D? Which 2D representation is useful here at the input or is beneficial for both accuracy and generalization? And now we will see at how much, where do I place these losses and how much 3D data versus 2D data do I need? Can I just get away by just using 2D data, or do I need a bit of 3D data? All right, so here are the errors. And so basically, like these errors are typical errors that you have in 3D pose and shape estimation. You have the 3D error in millimeters. You have like error in terms of PCK metric, and the error in terms of so the PCK measures like how often all the joints are within some percentage of the ground truth, right? Within some distance from the ground truth. And then here you have also the joint rotation error in measured in quaternion distance. So what is interesting here is that if you use only like a 2D loss and no prior, no GAN, like the HMR, the error is terrible, like 198. It means basically you have some good localization of the human, but not much beyond that, right? You're not doing anything meaningful here. If you have like a loss in the 3D joint space, in the Euclidean space, like the 3D error goes down drastically. Like you have 83.7. That's significant. And then basically like the problem with this loss here is that you're not measuring the orientation of the body. So therefore, this error in quaternion space 1.962 is still quite high, right? It's almost as high as this only using a 2D loss. Now, this LLAT is placing the loss on the latent space, on the pose and shape parameters directly, right? We have a loss directly on those parameters. So we have here that in terms of 3D joints, we are doing as well as with the L3D loss. But what is important here is that the joint quaternions, like the joint error measured in quaternion space, this measures the angular error, it decreases significantly from 1.9 to 0.2. And basically at the end, like combining the three losses is what gives the best results. But the important message here is that first, using 3 losses, of course, improves like 3D accuracy. And second, like if you place the loss in the latent space, it will measure both the position and the orientation error, right? All right, so now like the perhaps more interesting experiment, how much, because this is key, right? Is like how much 3D supervision do I need? How much can I get away with just 2D data? And what is shown in this plot, in the y-axis, we have the 3D error in millimeters. And on the x-axis, we have the percentage of training data that has ground truth, right? So essentially, when you start here, 100 means that all the data has ground truth annotation. So this is a controlled experiment for a data set where we have 3D ground truth, which was obtained. It was not easy, but it's a data set that's called the United People data set. And there are like there's 3D ground truth. And basically, so here, like we start with 100%. And then 50% means that 50% of the data has only 2D joints as annotation, but no 3D. And if we take, for example, 5%, it means that only, I think I said the thing the other way, sorry. Let me repeat, 100% means that all data has 3D annotations. 50% means that 50% of the data has only 2D annotations. 5% means that 95% of the data has only 2D annotations, and 5% has 3D annotation. So this x-axis tells you the amount of data that has 3D annotation. And what is interesting here is that the error is not going up quickly. On the contrary, it's staying more or less the same until you have like about less than 2% of 3D data. As soon as you have less than 2% of 3D data, the error goes up quite high. So the reading of this is that if you have a bit of 3D data in your training set, the network is like implicitly learning some sort of prior over pose and shape. And so so that's sufficient to regularize the network, and then the rest is learned from the 2D joints. So this is quite interesting because we are not using any prior here, and it's learning this exactly like from the data. This prior over pose and shape is learned from a few samples of 3D annotations. All right, so the key messages after investigating these research questions are that using an intermediate 2D representation is indeed useful, and using a small amount of 3D data is enough in conjunction with 2D annotations given by key points. In all of these methods, the bad news is that things saturate at some point. Like you would imagine that you would keep adding more and more data and things get better and better. But the truth is that at some point, things don't improve any longer. But until you get to that point, definitely having lots of 2D key point annotations and a bit of 3D data is useful. All right, so let me show you some results. So here's the semantic segmentation predicted from the image, and this is the reconstruction. So notice how the pose is quite sensible. However, the shape always looks a little bit average. And this is a problem with all these methods that are called human pose and shape, but they are actually almost only pose. The shape is like not very accurately reconstructed, especially the regression-based methods. All right, so the code for these methods is available. I'm not sure if this is it's been some years already, so I'm not sure if the packages are still up and running. But yeah, so these are some qualitative results. So we have like on the top row, like the best performing results, and then like the second best and third best, and lastly the failure mode. So basically these errors, these rows are sorted according to the error. So in the top, you have top 25% best results. Then you have like second best, so like from 25 to 50 and from 50 to 75. And then finally the worst 25%. All right. So after these methods, there was one method that basically it leverages the same idea, but it's maybe a little bit more direct. So essentially, it's noting that the regress shapes do not fit the image so well many times. So what they say is like, okay, this data is difficult to obtain, these 3D poses, but what we could do is like start with a deep network and then do optimization, which we know how to do, right? And obtain better fits, because we know that optimization works if it's well initialized, and now use these fits to supervise the deep network, and I will iterate this, right? And so that's the basic idea. You have like here a prediction, then you do optimization, and then you supervise the network with these predictions. So yeah, these ideas are similar to things we've seen for registration, where you optimize over one set of parameters, like holding the other ones fixed and so on, right? I mean, you should draw connections here between what we've seen and this. So yeah, this is maybe a more direct way of combining learning and optimization. All right, so these are some results. So these are results on a data set that is called the 3PW data set, which we recorded in Tübingen, and now it's one of the main data sets for evaluating like methods in the wild, and it's in Tübingen, so you can have a look and you will recognize many of the, yeah, you will recognize the background. All right, so in summary, I think the take-home messages for you are that optimization is providing very good accuracy if it's initialized well, and it has a feedback loop. This means that the estimates are always continuously verified against the image. So this is, in my opinion, is a very good thing. But they require initialization, and this is something that is very annoying. And for learning-based methods, the key problems are the lack of data. But once they are trained, they are automatic, and they leverage the data prior in the prediction. So this makes them it allows them to be automatic and not require initialization. However, they tend to be a little bit less accurate. We've seen that they often do not align with the image so well. It's because they do not have this feedback loop. All right, so we're almost finished. I just want to show you a little bit more mathematically what's the connection between model-based optimization and regression, and because actually they are not that different, right? So in all these methods that we've seen, these self-supervised methods, what we're doing is we're training a neural network to predict pose, shape, but you could extend it to predict clothing and texture. In fact, people have done this. So then you can have your model of the 3D world, or in this case of the 3D humans. So you could predict like the geometry and the texture, and basically combine things and have a differentiable renderer in order to explain the image back. And right, so that's the idea, right? And you have like these different components here, and essentially like this block here, right? What people have been doing classically is to optimize these latent parameters, pose, shape, and whatever latent parameters you have parameters for clothing. We will see how to get those. Then you could optimize those latent parameters in order to explain the image evidence. And essentially you had like here this optimization problem, arc mean over the latent parameters, theta, beta, and clothing, which minimizes the rendering loss or a pixel-wise difference between the rendered model. R is a rendering function that takes the simple model and it projects it into the image and it renders it. And then like this distance compares it against the image, right? But of course, this is a very local thing, like to compare pixels directly. So people have essentially like extracted features from the image. This is what we saw in the optimization lecture. So this Z here, Z hat could be silhouettes, edges, semantic segmentation, key points, and so on, so that this objective is better regularized, but still the optimization can be slow. It still requires initialization and basically assumes that well, I mean, this is a different topic, so let's skip that. And so what we're essentially doing here, right, with these self-supervised methods is to now we are parameterizing these latent parameters, theta, shape, and clothing as a function of the image itself and the neural network parameters, right? That's what we are doing here, because we are going from the image, getting the latent parameters, and then projecting them back, closing the loop. So essentially, we have an optimization problem like before. The only thing is that now the arc min goes over the network parameters, and potentially we could also optimize the parameters of our body model, right? We've seen how to do this during a registration, but maybe we could also do it using lots of images. Something that nobody has achieved so far, but conceptually it could be possible, something that I would be very interested to do. And yeah, you could optimize the network parameters and the model parameters in order to minimize this discrepancy between my model of the world and the world, right? So we have this this optimization. The only thing is that this optimization now is a learning problem. So we don't have a single instance optimization, but we have here a loss function over a training set. So you have like for every image in the training set, we want that our prediction of the world, all this block here, matches the images, right? The image, the specific instance. Yeah, so this is a really challenging problem, but the cool thing is that now we can leverage, like with this formulation, we could potentially leverage like lots of images and video in the internet in order to train like better regressors from image to these 3D world parameters and potentially better 3D models. So that's a conceptual formulation. In practice, there's many pieces that are that make this very hard. And what makes this very hard is that sometimes the signal to noise ratio is not very good. So you have like more noise in every new image that you add than you have signal in order to learn a model of bodies. For faces, people have trained like very good face models using in the wild data or improved existing face models. In practice, you always need a bit of 3D data, and like then the question is how to use the 2D data in order to make these models better. But conceptually, this is quite interesting, and you know there's still many things to do using these concepts. All right, so this comes to the conclusion. So we've seen that top-down top-down and optimization is basically used in this context like equivalently. So top-down optimization approaches require initialization and manual tuning of objective parameters and objective terms. And so bottom-up learning approaches are automatic, but they are not very accurate, or they do not align with the image so well. And we have hybrid approaches that combine optimization and learning in order to learn in a self-supervised manner without so many 3D labels, which are difficult to obtain. And we've seen that if you have limited data, it's very good to abstract appearance, to remove all the information, all the details that are not so relevant for your task. And we've seen that a small amount of 3D annotations are sufficient when used in conjunction with 2D annotations. Thank you very much. That's the end of the lecture. Bye-bye.